The last method I want to talk about is known as ordinary least squares regression. Colloquially, it's just known as regression. So you could call it regression analysis. It's not the best name because it's like saying, food. What do you want for dinner? I want food. Well, could you be a little bit more specific? No, I just want food. Okay. So regression is like that term food. It's not very specific. This is a type of regression, ordinary least squares regression. And to me, this is probably one of the more useful things that you'll learn because it applies for when you have a dependent variable that is continuous. So income, for example. All right, if you can count it, this is the type of analysis you should be doing. And it's great because you've already been taught ordinary least squares regression in high school and middle school, even if you never took a statistics class. Because you were taught how to graph dots, right? You were taught how to do things like this. All right. Here's a great example and an intuitive way to show you that you sort of already know how to do this. If we were to play a guessing game that asks you to guess a person's age, you should already right now know what your guess should be. If you want to guess a value of something, what should you pick? Hampton, pick a number between 1 and 10. Why 7? It's wrong, by the way, but why 7? Okay. Who has a better number to pick? Why 5, Aiden? All right. Because he's like, it's in the middle. It is the mean. Okay. That's our inclination. If you ever play a guessing game and you're asked to guess something, you should pick the mean. Now that requires you to have a piece of information, the mean. According to the CIA fact book, the average age of a person on whenever I wrote this slide was 38.5 years. So if I said I went to Joe's birthday party this weekend, guess how old Joe was this weekend. You should guess 30. You can have a birthday for 38.5? 38 or 39. All right? That would be a good guess. Why? Because most people, the mean, the most volume, the center of our curve, the highest point on the curve is 38.5. So you should pick 38 or 39. What number wouldn't you pick? Absolutely would be stupid to say this number out loud. No. No. 0. Why? You don't celebrate a 0th birthday. What do we call the 0th birthday? Birth. I went to Joe's birth party this weekend. I was there in the hospital room. All right, I cut the cord. I won the game, so I got to cut the cord. Right? You wouldn't say that. You wouldn't say 100. Why? Because you don't see a lot of 100-year-olds. And you definitely don't see 100-year-olds having a lot of parties. Although if I'm ever going to have a party, I'm going to have a party at 100. All right. So when we have sort of no idea, we should pick the measure of central tendency. Because why? That's the most. Remember? Mean, median, and mode, right? Measure of central tendency. We should pick the one that has the most observations. I'm going to give you one more piece of information. Right? I want you to guess my wife's age, and I will give you my age. Would that be helpful? Kinda. Why? Why? Yeah, usually we expect that people, when they get married, will marry people of similar ages. And when they don't, It's what? Weird, creepy, ew, gold digger, right? Pedophile, right? We go, huh? You're this age and she's that age? What? Okay. So we have an expectation. The way that the book likes to teach regression is in a correlation framework. I think correlation is stupid. And this is also one of the reasons why I wanted to teach a social science class rather than have the statisticians teach the stats class, is because the statisticians love correlation. But social science people don't like correlation. We like learning about this in another way. But to give you the correlation example, the concept of correlation holds that one observation that has two characteristics, those characteristics might move together if they're highly correlated. So when I clench my hands together, the movement of my left hand is influenced by the movement of my right hand, right? If I move my right hand, my left hand goes with it. That's a high amount of correlation. If I separate my hands and I move my right hand, does my left hand move?
No.
You sure? Okay. It moves a little, but not to the exact degree as when they're linked together. Or if I had like handcuffs on, I could wiggle my right hand and my left hand wouldn't move. And there's a way to do this in terms of correlation. We think that ages of spouses, do we think that it's highly correlated or not correlated? We think it's highly correlated, right? And we, in our minds, have an expectation that it's about a one-to-one correlation, right? So if I'm 20, my wife should be about 20. And as I age a year, she'll age a year. Okay? I don't like that because it's too much about focusing on the movement. I like to think about ordinary least squares in a framework that we're already knowing. Because when you were in middle school, you had like a month where your teacher had to hand out graph paper. And you learned all sorts of things in geometry using that graph paper, right? You want to show somebody the area of a square or a rectangle, have them draw a square or a rectangle, and then have them count the little units inside of it, right? Like 1 block, 2 blocks, 3 blocks, 4 blocks high, 3 times 4. That's 12. That's the area of a square. Not a square, a rectangle. Because if it's a square, it's got to be 4 times 4. Okay? And then, once you've mastered geometry through graph paper, they do a little add-in where they talk to you about lines. And what they really want to teach you is this. But they're not quite there. So they don't give you all of the dots. They just basically say, and this time you had this number, and at that time you had that number. How much did you change over time? That's like 2 dots. And they draw a line. And then you use your version of counting over and up to count how many, right? Usually you use the Pythagorean theorem, a squared plus b squared equals c squared, to find out the length of that. It's really only useful when you actually use it for something. So let's say this is an actual data cloud. And we're trying to predict my wife's age. And she's not here, so we can do that. And most of you, I don't think, have met her. Some of you have. If you have, stay out of this. You Carolina Forest kids might have met her. All right? So I will tell you my age if somebody will get a calculator out, because I don't know how old I am. You ready? What year is this? Minus, I've had my birthday, 1978. 39? All right, I'm 39 years old today. No, it's not my birthday, but today I'm 39. Earlier in the year, I wasn't 39. I was only 38. Today, I'm 39 years old. Guess how old my wife is?
36.
Everybody done? All right. If you wanted to have a really good guess, what did you say? I thought you said 23. I'm like, holy shit. All right. We're off the chart here. Okay. Now, I told you how old I was. I'm 39. So that is which row of dots? Where's my pen? Oh, damn it. Oh, there's my pen. 39 is this row of dots. My pen's tired. Let's try this again. There we go. Loose cap. All right. This row of dots. All right. Let's see. Oh, this worked better when I was 38. We're going to do this row of dots. Even though it's the 38 row, I don't care. 38 column, I don't care. All right. What would have been a reasonable guess? Well, anywhere from 32 to 41. Yeah. My wife's age is 40. I had one person say it. So the gap between my wife and I is, it's 14 months actually. There's a glorious time where she's 2 years older than I am. Do I ever what? No, I never do that. I have immediately pointed out that every time she complains about anything since she was 40, it's like, ooh, 40's a rough year, isn't it? Again, I'm not exactly a nice person. All right. Now, if somebody in this room, to be a jerk, would have said like 60, you would have lost a lot of money. Because do we see a lot of 39-year-olds with 60-year-olds? No. Okay. When do we see people that have 60-year-old wives? Well, you got this one person out here that's like 54. And then you've got some gentlemen that are in the 60 to 70 range. Like this guy's kind of an outlier. Okay. But for the most part, they move together. Right? We have a pretty high correlation. That's nice. And if you can calculate the amount of correlation, which tells us for a 1 unit increase in one, how much does the other one move? When have you done that before? This is where, again, you've already learned how to do this, but just not in a statistics cloud of dots way. Where have you sort of learned to describe the relationship of as X increases, Y also changes? Do you remember? Yeah, slope. But you didn't have a cloud of dots. What did you have? You had a line, right? So way back in 6th grade, you guys were taught what essentially regression is, but you were just taught it in a line, and you were asked to find the slope of the line. You see, this is what bothers me about teaching like math. You don't really understand why you need to use this, right? This is the #1 complaint about math when you're like in middle school and high school. When am I ever going to use this? Well, if you're a contractor and you try to calculate the pitch of a roof or the rise and run of a staircase, maybe, and then you're like, well, I'm never going to do that. Okay. Let's just teach you guys statistics. Or I can show you like how to win gambling games. Everybody likes that. Okay. So you were taught this concept, but you were taught it as the slope of a line. And what was the equation you were taught? Y equals mx plus b. Yeah. It's actually, that's a regression line. That's an ordinary least squares regression line. But because it's statistics, we got to change it a little bit. We got to change the letters around. We've been doing this for hundreds of years. It goes back, Legendre first used OLS in a published paper to predict the orbit of comets. I'm not a physicist, don't ask me to explain it. But it's there. Gauss is a mathematician, and once he reads Legendre's work, he's like, hey, I already did this, like a long time ago. Gauss is kind of a jerk. Like, not a jerk like me that says strange things, but kind of like a, hey, look at me kind of a jerk. Like, yeah, I'm so smart. Gauss claims he develops it, oh, I did that a long time ago. Like, that's easy. I didn't know that was a thing that I had to claim. Like, that's Gauss's kind of approach to this. But actually, we attribute it to Legendre because we adopt his name for it. And his name is the method of least squares. Because that's how we decide where to put the line. The line is an attempt to draw a single line through a cloud of dots such that the line is the best representation of all of the dots that we have. Right? The line represents the cloud the best. So in geometry or whatever the hell that math was, the slope of a line is equal to y equals mx plus b. M is what? M is the actual slope. X is actually the x, right, your data point. Plus b. Anybody remember what b was? The y-intercept. Okay. We rearrange these things. Y is still y. But in reality, when we do it, we're actually trying to predict that value of y, right? We're trying to predict my wife's age. We put a hat on it. So it's y hat. Little carrot shape. So if you're predicting a value of y, you're predicting y hat. mx plus b. X is still x. X is still that value of x that you're putting into the equation to find where the y is. X is our independent variable. X is our measure of income. If we're trying to, oh wait, sorry. What was the example we used? Oh, education. All right. X is the number of years of education. Sometimes that B, we actually call that something else. Some textbooks use beta 0. Others use alpha. I don't know why. There's no really rhyme or different reason between the two. I understand why you would call it beta 0 because it is technically a coefficient that you're generating through the prediction, but it's not a slopey one, right? It's a starting point. And what's the starting point of an alphabet? Or alpha. So that's why you can remember it as alpha, the starting point. The starting point on drawing the line is figuring out where it starts on the y-intercept. I like alpha, but again, you might see it as beta 0. The one other thing that we put in here is this little epsilon, this little e. These represent the errors. Now, for the most part, we think the errors will cancel each other out. So I know your textbook in Takunda, he doesn't put the e in the equation because it's not something you actually calculate. But it's there. There's just a little bit of error. There's a little bit of, in the Tuesday class, we called it Alabama, after Roy Moore, right? So we might have an expectation that the husband's age and the wife's age should be about the same, but there could be a little bit of Alabama there, where it's okay to have like a 15, 16-year age gap, right? You're 32, she's 16. What? Right? Well, it's a timely example, right? That's when Roy Moore said he first noticed his wife when she was 16. She didn't actually start dating her till she was in her 20s, but, you know, I first noticed her when she was 16, kept my eye on her. Okay. Let's just call that the Alabama effect. Or a gold digger effect. All right? There are lots of situations in which we can, and we name a significant age gap. That's our errors. It doesn't apply to everybody, right? But there are some out there that are, you know, purposely interested in preserving that age gap. Wasn't there like a TLC show, like where they bring out people and it was like the guy was in his 20s and the lady was in her 60s or 70s? And they're like, yeah, we don't want to watch this. So it only lasted one episode. Turns out people weren't that interested in it. It's like, no, let's go back to the little people. All right. So that's our error. Our error could be the fact that we don't have perfect correlation, right? That we as human beings aren't deterministic. That there's no law in place that says you can only marry somebody within a 1-year age of you. Right? It has to be a less than 12-month difference. We don't have that law in place. We don't have that custom in place. So there's going to be variation. There's going to be errors. Okay. That beta is our slope. So that coefficient that we generate, the beta, is the old m. Y increases as x increases. If it's a positive beta, I have to, all right, so if as x increases, the effect is that y also increases. By how much? Beta is the amount. The sign of the beta tells us the slope of the line, because slopes can be what or what? Okay. Slope can be a positive number, a negative number. There's actually a third option. What's a number that's neither positive nor negative? If you have a zero line or a zero slope, you are, yeah. So as x increases by 1 unit, y increases by 0. There's no effect, right? In that case, the correlation is actually 0. Right? So as I move my right hand, what happens to Alex's left hand? Nothing. Why? Because they're not physically attached to each other at all. Nope, didn't move. Nope. Didn't move again. There should be no relationship. The thing about ordinary least squares is it is numbers based. If you put an ordinal variable in there that is measured from 1 to 5, it'll treat it as if it's continuous. If you put a nominal variable in there where you assign Catholics to 3, Buddhists to 50, it will go ahead and do it. And it'll say that as X increases, you get a Y unit increase, even if Y isn't a unit that can increase. Right? Because you don't like get +1 to go from Catholic to Jewish. Like, it doesn't work that way. But if you tell it, hey, analyze this data, it will absolutely do it. The results will be complete nonsense. The same thing with a dummy variable, right? If we treat gender as a 0, 1 dummy variable, and we say that as you increase your income by 1 unit, how much is, like, making more money makes you 0.05 more of a man? Like, as you move from 0 to 1? But you can do it. Like, you can mathematically do it. So this is why when you guys are like, well, I'm not sure what I use. Well, what you use is totally dependent upon the information and the shape of your data. Because OLS, like I said, it will do anything. If you have 2 numbers, it'll say, I can do that. I can put them in a cloud. I can draw a line, even if the line makes no sense. OLS will do it. So you have to be careful in when you use it. Because you might be using it when you shouldn't be, because it doesn't make any sense to use it. The math isn't that hard. And it's great because you actually aren't going to be doing the math anymore. Once you've graduated to thinking about doing stuff with OLS, it's time to let the computer take over. It's time to use statistical software. Because doing this for 1,200 observations, you have to do it observation by observation by observation. Because you'll notice those little subscript i's, those are each individual observation. So x of I, you put a number in there, x1, that's the first observation. You put x2394, it's the 2094th observation. I was taught how to do OLS by hand. Hours it takes to do the thing that I pulled up that had 9 observations. Hours just to do 9 observations. You're not going to be doing that. Now, when I say it's time to let the computer take over, that's a good thing. But it also requires something of you. You actually have to learn a program that does statistics. You can do ordinary least squares regression in Excel. It is possible. Man, I hate it though. Because you're right on the edge, right? You're right there in becoming an actual statistician. It might be time to upgrade your tools. You really should consider it. My dad was a mechanic. Did I tell you the story of the 3-inch nut socket? My dad was a mechanic at a paper mill. He was called a millwright. And my dad had the ability to fix any machine in that mill, whether it was a conveyor belt, whether it was a pulper, whether it was the machine that stripped the bark off of something. It could have been the locomotive that drug the coals in, the coal trains in. It could have been one of the finishing things that spins around and, you know, stretches the paper out and wraps it up. My dad, his job was to fix the mill. And when Dad died, we had so many tools. My mom lives in a house up in the Adirondack Park in New York. She doesn't live in a paper mill. Like, she doesn't need, my dad had these. He had a socket set. One of the sockets was for a 3-inch nut. My mom's like, do you want this? No. I'm never going to come across in my daily life a nut that big. Right? They don't even make buildings where they put the girders together and they're not even that big. But somewhere in that mill, there was a 3-inch nut, and he had a socket for it. Actually had 3 sockets for it because he had 3 different sets. My dad needed to use those tools because that was his job. That was his specialty. If you guys are going to claim that you have statistical skills, you might need a 3-inch socket. And that might be learning a program and then this is what the next video is going to be. It's going to show you guys some of the options that are out there that are available. I'll show you SPSS, which Coastal has in the computer labs. It's just like Excel, but actually designed to do statistics. I'm going to show you Stata, which is what I use on a daily basis. And then I'll show you the free version of a program called R, which is what real mathematicians use, but it's free, so students should figure out how to use it too. So you're not going to do this stuff by hand, but I just want to show it to you because you have some literacy now on what's going on. Beta 1, the slope, is the sum of the difference from the mean of each individual observation, right, divided by the sum of the differences in the x's. So really what we have here is we've got this amount of variation and covariation. The way that the textbook explains it is we know variation, right? We've understand variance since chapter 4. It's how much one changes. So when we do x minus x bar, that's the variance. That's how much x varies. But what we try to do is see how much x varies relative to how much y varies. And that's known as covariance. Best example I can think of to explain to you covariance is the relationship between height and weight. We would expect that children, as they get taller, they would get heavier. And we have growth charts that are built around this idea. So when I take John to the pediatrician for his yearly checkup, they see how tall he is, they plot that, and then they plot his weight, because when you're, well, no, this tall, you should be 40 pounds. They don't do it by age, they actually do it by height. They don't care how tall he is at his age, they just care, all right, given your height, how much should you weigh? Not how old are you, how much should you weigh? Because it's a function of height. That's why they measure both. And they have these growth charts.
What's the difference in covariance and correlation?
Not much. Okay. So what we need to do is we need to figure out the covariance, because there is movement together. So the correlation is what causes the covariance. Okay. Again, I'm not a big fan of the whole correlation thing, because again, it's confusing. But if you just look at it, and remember, the whole point of OLS is to draw the magic line, right? That best fit line. What we're doing is we're figuring out where to place the line such that the gap between what we observe, right, our actual data point, and what we predict through the y-hat equation, we're trying to reduce the amount we want to find the line that minimizes all of the explained area. Because you are going to have unexplained area. You are going to have the Alabama effect, the gold digger effect, the fact that I just don't care about age. It's just a number. Okay. So what we're really, we're really trying to do is to minimize how much unexplained there is. Now I can do that with one dot. Just draw the line right through the dot, right? But how do I do that with a cloud of dots? I have to take into account all of the gaps between my line and my observed. That's what this does. Because you do it for each individual observation, you're essentially calculating the best slope for all of the data points. Last slide, and then my last minute, and I'll let you go. So when we have, if we look at here of it, a perfect relationship. So this is something that is deterministic, right? A 1 unit increase in X results in a absolutely blank unit increase in Y. All the dots are actually making a line. That's perfect correlation. There's not a lot of gaps there, right? There's not a lot of distance between the predicted line and the actual observation. But if you look at something like this cloud that has a strong relationship, we draw a line through it, there's going to be gaps between the dots and the line. That line is the least amount of gaps, the smallest amount of residuals. Okay. As our correlation gets weaker, notice the shape of the cloud. So perfect is a line, pretty good is like an oval, okay is an egg, really bad is like this circle. Like, how am I going to draw a line through this circle to minimize the dots? It's going to be flat, because the best predictor is going to be the mean, which we learned way back in chapter 3, and which is how I started our guessing game. So that's ordinary least squares. Watch the video. I'm going to take a data set and I'm going to do it in different programs, so that way you can see how you would actually do it to compute the values. Last thing, SDA website will do this. There is a tab for linear regression.